Hello. For the power resonance, we still stick with the concept of resonance. Resonance is a phenomenon when XL is equal to XC. But this time, we are in parallel resonance. It means they are connected in parallel instead of in series. So if this is R, then we have L, then we have the capacitor C. So R, L, and C. So they are connected in parallel. Now, if this is the case, still for a resonance, this should be true. XL is equal to XC. So what happens to L and C when this is true? Then this L and C combination will act as an open circuit because we only want the pure resistive part, just like in RLC, the series combination of the L and C will become just a short circuit. So now that X of L is still equal to XC, but the formula for the Z is not the same again with the series resonance, but we know that Z, we can use the other properties. Z, the inverse of Z, which is just equal to the admittance. Instead of impedance, we look at the admittance. In series circuit, in series resonance, the imaginary part of Z will become 0, X of L, because Z is equal to R plus JXL minus XC. This will become 0. This is the imaginary part of Z. Well, for the parallel resonance, instead of the impedance, we talk about this one, Y, the admittance. You already discussed this in circuits 1, Y, admittance. And the imaginary component of this should be equal to 0. R plus J XL minus XC. XC. And for resonance, this become 0. So it's not impedance, which is equal to R, but the admittance will become equal to the R. And for the derivation of the properties for the frequency response for RLC or for parallel RLC circuit, if you look at the lower and the upper cut of frequencies, we can use the duality property of this series and parallel resonance. In series, omega L is just equal to negative R over 2L plus the square root of R over 2L squared plus 1 over LC. So what we do in the parallel resonance, we just change R with 1 over R and also L with C. And the result will be, so this will become negative, R will become 1 over R, so 1 over R, 1 over R, and we have 2 there and R, then L will become C. So 1 over 2 R times C. And we do that again here. So this will become 1 over 2 RC squared plus 1 over LC. So this will be for the lower cutoff frequency. For the upper cutoff frequency, it's the same thing. This will become positive. So 1 over 2 RC plus the square root of 1 over 2 RC squared plus 1 over LC. So if you want to solve for the bandwidth in terms of this one, the frequency, natural frequency, will be just equal to, you subtract this, so 1 over the 1/2. So that's just R times C. So if you want to include again the resonant frequency here, the frequency, you multiply the frequency so that we can solve for the quality factor. And what will be the quality factor for this one? We can derive it from here. This will be, you can multiply this with omega R, the resonant frequency, then this will become 1 over omega RC. And if you do that, that is just equal to what? Omega over the bandwidth, or the Q, quality factor, quality factor, which is just equal to omega R times R C. Or we can also rewrite this in terms of the L. So we just, instead of C, if you want that in terms of L, so that will be R all over omega naught, or omega R times L. So the relationship still, you can just divide this bandwidth, or omega R with the bandwidth, so to get the Q factor. Q factor is just equal to the bandwidth, or the resonant frequency, omega R, all over the bandwidth. So these are formulas you can use later on when we take our examples for the two phenomenon, the resonance in series and parallel circuit. So if we summarize the two, a series circuit and the parallel circuit, parallel. So for omega R, our formula in the series circuit is 1 over the square root of L times C. For parallel, I forgot to derive that parallel, because XL is just equal to XC again, and then this will be omega R times L equals 1 over omega R times C. So it's just the same thing,